I'm going to set up a quick water simulation. And then I'm going to have this box collide with it. So let's start with the simulation. I'm just going to put down a box. That's going to be my water tank. Going to give it some size, 5 times 5 times 5. And then I want to fill its bottom part with water, so I'm going to clip it. And I want to clip in the direction of y is 1, actually y is -1. And then to close it, I'm just going to put down a polycap. And then I'm going to fill this with particles. So I'm going to put down a point from volume. And we have a bunch of particles. And then put down a null. And it's going to be my water source. And I also want to use this box as a bounding box. So I'm going to create a null for that. And this is the bounding box. I'm going to reference both of these nulls inside the dot network. So now I'll put down the dot network. Dive inside. I'm going to put down a flip object. And I'm going to use a particle field. And then I'm going to point it to the water source null. So out of this node, up one level, and I called it water source. So that is this one here. So we have the water in here. And I'm going to put down a flip solver. Connect it and move the orange flag. Give it some gravity. So now the water falls down. I'm going to change the particle guides to particles. So in volume motion, I have the volume limits here. And I want to reference the size of this null here bounding box. To do that, I'm going to use an expression. So it's a bbox, and then out of this node, up one level, and then I want the bounding box null. So you can see here, you can reference the size of x as d underscore x size. So uppercase D x size. Then I'm just going to copy this one and change it to the y size. And then change it to the z size. I also want to reference the center because I think I'm going to be moving this box around. So to do that, I can use a centroid expression. And I want the same node. Out of this node, off one level, and the node is called bounding box. And again, you can see what you need. So I want the center of x, d underscore x. I'm just going to copy paste this, d underscore y, and d underscore z. So now if I change this box, this will update as well. The water will fall through the box, so I'm going to go back to the flip object and close the boundaries. So we got some water. Now let's bring in the box. So I got it up here. I will put at the end of this video how I created this box, and I also will put the Olympic in the description if you just want to download it. I want to make my water a little bit more shallow, so I'm just going to move this box up in Y. And then let's take a look at the box. So it falls a little bit to the side. So I guess I just wanted to land in the water. So I'm just going to put down a transform. And let's just merge these together just to take a look at it. So I'm just going to move it a little bit to the side and maybe a little bit down. So it's kind of landing inside the water. Right now this box is still packed, so I'm going to put down a unpack node. We got some attributes, velocity and angular velocity, but I'm just going to delete them. To delete all of the attributes, I can just say delete non-selected and then not choose anything, so we don't have any attributes anymore. Then I'm going to use a trail to calculate the velocity again. And I'm going to say compute velocity. Probably the old velocities were fine. I'm just recalculating them just in case. Then I'm going to put down two nulls. One of them is going to be for the geometry. This one. I'm just going to call it collide geo. And then I'm also going to create a VTB. So I'm going to put down a VTB from polygons. And this VTB is going to help us with the collision. And in here I have to give it a voxel size, and ideally I would like the voxel size of the collider to be something close to the voxel size of the simulation, or the surface field of the simulation. And that is set to be 2 times the particle separation, so that is 0.2. Or if you check in the geometry spreadsheet, you got the surface field, and it has the division size of 0.2. So I'm also going to set the voxel size of the collider to 0.2. Then I'm going to put down another null. And I'm just going to call this collide VDB. Now inside of the dot network, I'm going to put down a static object. And I'm going to pick up the box here. So out of this node, up one level, and the null is called collide geo. There is this null here. And then I'm going to hook it up to the node tree with the merge node. And notice the affector relationship is left input affects right input. So I'm going to make sure the static object is on the left here. And now if you look in the geometry spreadsheet, you can see we have another object. That is this static object. And it takes its name from this node. Now if we play the simulation, nothing happens to the box, and that is because we need to toggle use deforming geometry. So if we do this, it will expect the box to move on every frame. Otherwise it would just read it in on the creation frame and keep it the same. So now if we play the simulation, the box actually hits the water. Inside of collision, you can see we have some option for collision detection set to use solver default. And the default of the flip solver is a volume collision. So you can either just keep it as default or set it to use volume collision. And the box that you're seeing in the scene view right now is not the actual box that will be simulated. The actual simulated box is this one. So I recommend always checking out the collision guide. Here you also have the option to bring in a proxy volume. Right now it's creating this box according to these rules, but if you just want to take whatever this VDB is up here and use that, which is not particularly useful for this box, but would be very useful for some more complex colliders, you can use a proxy volume. And this is where we will point to the collide VDB node, this one. So we go out of this node, up one level, and then it's called collide VDB. And then we should just match whatever the voxel size is in here. So I'm going to set the mode to volume sample, and then I'm going to set the division method to by size. And then we can just set the division size, and I'm going to set it to 2 just to match whatever we have up here, and also the voxel size of the simulation. And as we increase the resolution of the simulation, we will also increase the resolution of the collider, and this will be closer to whatever the collider is up here. So I'm going to hide the collision guide again and just show the display geometry. This node inherits the velocity from the box up here. So if you would like it to make a stronger impact on the water, you can increase the box velocities. So let's try it by putting down an attribute wrangle. And we can say something like multiply the velocity, so times equal by 2. And now the velocities are longer. And let's see what effects this has on the simulation. And if we play, you can see it makes a much stronger impact. Likewise, we can take it in the other direction. So we can decrease the impact. So I'm going to multiply it by 0.5. And now if we play the simulation, there is way less blasting going on. This is a very simple way to art direct your water simulation. For example, I can add some coral noise to the velocities. So first of all, I'm gonna remesh the box so we have a bit more points to work with. Maybe give it the target size of 0.05 meters, so there is 5 centimeters between these triangles. And then I'm gonna put down an attribute swap. And let's take a look at the velocities again. I'm just gonna take this attribute wrangle to 1. So it's doing nothing. We can actually just skip it. Let's do this. And then let's visualize the velocities. So if we go a few frames forward, you can see we have some velocities. Just don't put the trail after the remesh node because that's going to mess up the velocities because the point count is not consistent anymore. So inside of here, I'm going to put down a coral noise. So I'm going to plug P into position, and then I'm just going to write it out to V velocity to start with. Let's see what's doing. Okay, doing something. I'm going to take the roughness to 0 and then increase the frequency a little bit. Maybe you want it to be animated. So I'm going to pick up the time and then I'm going to put down a float to vector. And then I'm going to feed this into the offset. And now it's animated. If you wanted to go faster, you can multiply this by a number higher than 1. And if you wanted to go slower, you can multiply it by a number lower than 1. I think I'm going to give it a little bit of roughness back. Let's see, something like this. Now if we disconnect this one again, I only want this coral noise to be applied when the box is moving. So I don't want anything to happen when the box is still. So I'm just going to check the length of the velocity. And let's plug it into color. And if we hide the velocity vectors, you can see it's black when it's still and it becomes white when it's moving. That means when it's still, the length of the velocity is 0. And when it's moving, the length of the velocity is above 0, in this case from 3 to 10. And then when it's still again, it goes back to almost 0. So if we visualize the velocities again and get rid of this color, we can just multiply this coral noise with the length. And now if we connect this to the velocities, you can see we have a lot of coral noise when the box is moving, and then it gets less and less until the box is still. I think this is too much velocity, so I'm just going to take the amplitude down. Maybe we just want a little bit. And then instead of overwriting the velocity, I want to add to it. So I'm going to put down an add node. I'm going to plug the incoming velocity from up here into that node, and then the coral noise, and then I'm going to export that into V. So you can see now we have a more interesting velocity vector. And then you can go back to the coral noise and choose if you want more of this noisy look or less of it. Let's see how this affects the simulation. So I'm going to hide the vectors again and go back into the dot network. And let's play the simulation. So I recommend using the velocity of the collider to kind of sculpt your splashes. So let's go ahead and increase the resolution of the simulation. So this time I'm going to just start inside of the simulation. And I'm going to set the particle separation to 3 centimeters or 0.03. So then I'm going to copy this parameter by right-clicking on it. And then up here in the points from volume, I'm going to paste this value into the point separation. So right-click, and I'm going to say paste a relative reference. So this is going to go into the dot network, find the flip object node, and take the particle separation parameter. Then I also want to use this value to set the voxel size of the collider. So I'm going to paste it in here, paste relative reference. And then I want to multiply it by the grid scale. And the grid scale is 2. So I'm going to copy this value, and in here I'm going to multiply, and then right click and again paste relative reference, and this is 0.06 or 6 centimeters. And you can see also the collision object is a bit higher resolution in here. And let's play it again. A little slower. I'm gonna find an angle for a camera. Maybe here. New camera. And back in here. You can play it. And you can see how the water is colliding with the walls of the bounding box. On the flip solver, we do have the option to use a waterline. And if we do that, the water will only collide with the bounding box below the waterline. So if I toggle this, we get an option for the waterline, and I'm just going to keep it at 0. So that is right here. And now if we play the simulation again, you can see that the water is clearly colliding beneath Y, but up here it just goes through. Let's make a quick flipbook. I'm gonna uncheck these two and start. Yeah. I think I might actually want to move the box a little bit. So I'm just gonna go up here, and I want to move it a little closer. And here, I'm gonna move it in X a little closer so it lands further inside the water. Well, let's try it again. To create a box like that, I just put down a box, moved it a little bit up in Y, so 1 meter up. Then I gave it some initial velocity. So if we put down an attribute walk, dive inside, and I'm just going to put down a constant. And it's a vector because velocity is a vector. And let's just push it to the right, let's say 6, and plug it into V. And then I'm going to put down a RBD configure. And I'm going to plug it into the first input and the third input. So this is the render geometry, and this is the proxy geometry that's actually simulated. And I think if you don't connect this one, it will just take this one, but it's better to connect it. This prepares all the attributes and everything that you can see down here. And then I'm going to run this through RBD bullet solver. So I'm just going to connect these two. And now it's just going to keep falling. So I'm going to go and add the ground inside of collision. I'm going to add the ground plane. And now if we play it, let's try to get a bit more interesting. So inside of the attribute walk, where I set the velocity, I'm going to push it also upwards. And then I want to give it some angular velocity. So I'm going to put down another constant. And it's a vector. And the angular velocity is W. So if you look in here, you can see that it's going to transfer these attributes from whatever is up here to whatever is down here. And there is velocity and then also angular velocity. And whatever other attributes you would want to transfer, you can add here as well. So in here, I'm going to put down a bind export to create the attribute. And it's a vector attribute. And it's called W. Let's connect it. You can see it down here. And I'm just going to have it spinning around Y, maybe. And then maybe also around X. Let's see how this looks. Yeah, something like this. Or you can tweak the values, figure out whatever motion you like. Then to write it out to an Olympic, I'm just going to put down a wrap Olympic output node and connect it. And I want to render the full frame range. Give it a name. Let's just call it collider box and save to disk. So yeah, we will have this box next to our HIP file here. And then we can just use an Olympic node to get it.